And welcome back, my AP Calculus friends. Mr. Record here from Avon High School. And in this video, we are going to continue our awesome discussion about topic 1.3, which is primarily focused on finding the limits given a graph. But this time we're going to have to use a little bit of technology to make that graph appear. So we're going to get a good calculator workout here. But the most important part of this video is really going to occur at the end. So be sure to stick around because we're going to talk about the all-important 3 reasons why a limit will fail to exist. So let's get techie with this and grab our calculators and take a look at examples 8 through 11. So here are the notes for my students at Avon High School, and examples 8 through 11 say use a graphing utility when necessary to find each limit. We're going to go ahead and use a graphing utility for each one of these problems. And so for example 8, notice that we have a fairly complex function here. It's a rational function, a fraction, and we're going to find the limit as x approaches 0. So let's take a look at our graphing calculator software and get right to it. So here we are using our typical TI Inspire software. I'm down here now. Make sure you realize that if you are watching this video outside of Avon, maybe you're using a TI-84, maybe you're using Desmos, those graphing utilities would work fine as well. So you can see I've entered this function into my f1 of x equal menu. It is a function. It wasn't very difficult to enter just using the fraction template. And it does reveal this curve. Curve has got some very interesting characteristics, as you don't see much curve over here, which means that the domain is restricted. And I think having values of x less than 1 are going to cause a bit of a problem down here. You're going to get a negative under a square root, and we know that we can't have that going on. And then the other thing that I want to point out is that this graph is very limited. It's kind of lying to us. If you think about this denominator a little bit more, there is a value for x that also does not exist in the domain that is larger than -1. And that value is 0. Notice if you were to let x equal 0, the denominator would be 0 as well. And so by virtue of that, there technically would be an open circle or a hole right there. But it really doesn't make any difference of whether that hole appears or not on our graphing calculator rendering of this function, because the limit as x approaches 0 is going to be the value of 2 regardless. See how we approach from the right, we get close to a y value of 2, and at the same time we approach 0 from the left, we're going to be converging upon this y value of 2. So 2 is our limit to example 8. So there really isn't much more to it. We know that this is going to have a value equal to 2. The limit does exist. And we can now move on to our next function. And I got a good one here for you. When you look at example number 9, you'll notice that it is certainly a piecewise function. F of x is defined to be 1 whenever x is not equal to 2, but then f of x is defined to be 0 whenever x equals 2. And I want to point out or emphasize that we're going to find the limit as x approaches 2. So remember, 2 is our target for x. Here's our piecewise function. Can we input a function like this into the graphing calculator? And the answer is yes, we can. So let's take a look at our software. Now you'll note here that I did not enter this function yet into the calculator because I wanted to walk you through at least how to do that with the software or the handheld that I'm talking about, and that is the TI Inspire. Now the procedure is going to be a little bit different if you're using the TI-84 or Desmos, and we can briefly discuss what those look like here in a moment. But if you're going to enter a function, you could go ahead and hit the tab button, which is sort of the shortcut to get to the graph entry line. It will default as a function if that's the last thing that you are entering into the calculator. And in our F2 line, I'm going to put a piecewise template. That template is first of all the button next to 9, and then the piecewise function template that I want is this guy right here. It's the 7th one from the left in the top row. This will give you a 2-piece piecewise function. On the other hand, this guy would be a 3 or more piecewise function, and these two are very different. These are system of equations, so you don't want to use those. So we'll choose this option. I'll click again, and there it is, my piecewise function template. If you recall, our function was to say f of x is equal to 1 when x is not equal to 2. Not equal is found by hitting Control equal, and the inequality in the top row, far right, is the one that you're going to go with. And then for the bottom part, f of x is 0 whenever x equals 2. And that's going to be all it's going to take to graph this, unfortunately, erroneous piecewise function. Now I said erroneous, there's an error. And again, the error is just something that the graphing calculator cannot avoid. When we say that the f of x is equal to 1 whenever x is not 2, well then it stands pretty clear that you have these 1's all the way across, all these points infinitely close together, but by the time you get to 2, there should not be a point right there above my cursor. And so there technically would be an open circle there. Moreover, when x is 2, f of x is 0. So that means that there should be an ordered pair right above that arrow at the ordered pair 2, 0. There should be a point there. But again, that doesn't make any difference, because when it comes to finding the answer to the limit as x approaches 2, our answer is going to be 1, regardless if there was an open circle here or a complete continuous line. So the limit is going to be positive 1. Now, before we go back to the document, for those of you that might be using the TI-84, if you have a recent operating system upgrade, you should be able to access your piecewise function template by hitting Math, going over to Num, N-U-M, and if you cursor almost towards the bottom, you should see an option that says piecewise. And then from there, it'll look very similar to what you just saw here. If you're using Desmos, which is a wonderful tool, it's very different. In Desmos, you have to use braces after your function entry line to denote the domain restriction. And probably the best way to bring yourself up to speed is just Google how to enter a piecewise function into Desmos, and you'll see a gazillion different videos from idiots like me that want to help you out a little bit with that. All right, let's go ahead and return back to the document. And if you recall, we said that the answer is positive 1. Now we got things really moving right along. We're going to jump over to example 10, the limit as x approaches 0 of the absolute value of x divided by x. Now, if you're one of my students in my classes at Avon High School, this might look a little familiar to you. You might be thinking, wait a minute, where have I seen this expression before? Well, that was a very prominent feature of our summer packet that you had to sketch a graph of, the absolute value of x over x. And it's a really important graph because it has a lot of very interesting calculus to it. And we're going to continue to talk about those interesting things as the year progresses. But for right now, I want to sketch this graph and take a good look and see if we can find its limit as x approaches 0. Well, here we are once again. I didn't mess around. I went ahead and took the liberty of graphing absolute value of x over x right there above. And you can see that it's a very interesting situation. We have this horizontal line at -1, and we have this horizontal line at +1 on either side of the y-axis. Now, I want to kind of tell you something, because some of you might be getting kind of excited because, whoa, 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 there's an open circle right here, isn't there? Well, that didn't appear just by sketching this graph. That's a little trickery that I've invoked from using some features of the TI Inspire. So it's not a big deal because you don't need those open circles to find this limit as x approaches 0. But I want to talk about two things. First of all, why are there open circles? And then secondly, what is this limit? So the reason why we have an open circle here, and we technically would have one here as well, is because x can never take on a value of 0. It's not in the domain of this function. And so we have to define the end behavior of these segments somehow. And we would do that typically with an open circle or a closed circle. And so the open circle is the way to go. Now, if you're wondering, well, how did he get that open circle? Because that's kind of cool, and I would like to be like Mr. Record, because really, that doesn't even sound right. Anyhow, maybe you think you want to put that open circle there because you want the graph to look really, really nice. So a really cool way to do this, as long as you're in a document, you have to do this from a document on the Inspire. You can't do it from a scratch pad. Is you would go Menu, Geometry. Notice the Geometry feature is available when you're in a document. And you'll choose Points and Lines and Point On. That's a lot of things. Geometry, Points and Lines, Point On. Let's point to the part of the graph where you want that point. Slide it over to where it's going to be. We can only get it so close to the y-axis, and unfortunately it's like, oh gosh, that's not a y value of 0, but it's close enough. I'm going to go ahead and just hide this so we don't get kind of distracted. And then if you're like, wait, that's not an open circle. No, it's not. If you hover over it, hit Control Menu, you can change its attributes to a lot of different things. And I'm going to go with option number 9, empty and large. Empty and large. And then if you're not real happy with its color, after all, it's black, the rest of the graph is green, you could also hover over it, Control Menu again, and you could go down to option B, color, line color, right? Just above me, line color. And then let's go for this beautiful green. And now we have really what's the best rendition of this graph. But it doesn't matter, you guys, because the limit either way is going to be does not exist. Notice as x approaches 0 from the left, the y not only approaches -1, but it flat out is -1. And as we approach 0 from the right, we have a value that's always equivalent to +1. And because those two answers aren't in agreement, the limit doesn't exist. So that's what we're going to say here. Does not exist. We can use the abbreviation for does not exist. I generally would prefer that my students write out their words and phrases, but for the purpose of the video, I'm going to abbreviate. Now we come to the final graph, and I'm going to tell you, I shouldn't be playing favorites, but it's my favorite graph of all the ones on this page because it's so darn interesting. The limit as x approaches 0 of the sine of 1 over x. So if we take a look at this guy, first of all, let's denote that x is approaching 0. That's what we're going to have to remember. And it's likely that you probably don't have a lot of understanding, recollection of what the sine of 1 over x is because you may have never graphed it in your life. It's not something that typically shows up in a trig class. So let's go to the calculator and check it out. All right, so here we are. Notice that I don't have the graph already sketched because I'm trying to build the excitement. I can tell you're very excited. Don't try to hide that. I know you are. So let's go ahead and pull up our entry line by hitting Tab. This is the fourth function that we're graphing. So we're going to go into here and we're going to type in the sine of 1 over x. So we'll go into the trig menu. And when we do that, we can pull up the sine function. And then we can bring a fraction template in if we want. You could also hit 1/x. And there we have it. And we're about to hit enter to see what we've got. Remember, x approaches 0. Okay, well that's kind of interesting. And I'm going to change this color so it stands out just a little bit. Let's go with this pretty brown so that it matches the example number up there. X approaches 0. Well, let's see what's happening here. If I approach 0 from the left side, I kind of like drop down and then I go back up and then I drop down and I go, I don't know, somewhere around in here. If I do the same thing over here, I drop down and go back up and drop down. Well, I'll tell you what. If I were to ask you all, what do you think this limit's going to be? It's very likely that you could all say the same thing. And you could also say the same wrong thing. And oftentimes when I ask students this, they will say 0 is the answer. And I will tell you that 0 is incorrect. And the reason it's incorrect can be shown by getting a better look at what's happening right here. And so I'm going to zoom in. I'm going to use a feature that most graphing calculators have. And the TI Inspire, it's found in the menu, Window Zoom, and I'm going to choose Zoom In. Notice once I select that, I am in the zoom in mode, as the indicator in the upper left corner says. And if I position this little magnifying glass on where I want the center of the screen to be, it seems like the origin might be the best place than any. And then all I have to do is hit the enter button. That will zoom in 2.5 times, and you're still in that zoom mode, so you can just continue to hit enter over and over and over. And so I'm going to zoom 5, 6, 7. I'm just having a great time with this. 8, 9. Let's go even 10. How's that? And so that's 10 zooms. What do you guys think? Isn't it perfectly crystal clear? What are you going to say the limit is? Looks like we're at Walmart getting ready to check out, right? Boop. Looks like a barcode, for crying out loud, right? I can't even see you guys anymore. So let's go back to standard mode and see if we can get you a little bit better understanding. So by standard mode, I'm just saying going into Windows Zoom and Zoom Standard. So this is our original graph. Woo! Oh, now I can see you guys again. So what's really happening right there? Well, if you think of my nose as being the origin, all right, y-axis right here, x-axis going across. This graph is kind of doing something like this. It's coming from either side, one's above, one's below the x-axis, and they just kind of trade places as they get closer and closer and closer to my nose. But you're going to find out they're going to be in this perpetual state of moving up and down, and they'll never really converge towards each other to constitute the answer to some limit. They're in this constant state of up, down, up, down. And because of that, this limit, you guessed it, does not exist. It's a very unusual limit. We're going to try to give you some insight as to why it doesn't exist. Let's go back to the document. As we said, this guy is another does not exist. Now, honestly, the larger purpose of this video is to talk more about why some limits don't exist. Obviously, we have a pair here among these 4. What's making these not exist? And so that's where this part of the notes comes into play. Anytime in my notes when you see a box that's shaded in with some color, that means that the stuff in that box is very important and it should probably be looked at a second and third time as you prepare for quizzes and tests. So why limits fail to exist? There are really 3 reasons. And the first reason says, f of x may approach a different number from the right than it approaches from the left. So I'm going to highlight just the key components. F of x approaches a different number from the right than it does from the left. Something that we see quite often with functions with these jump discontinuities. Maybe you remember that phrase from a pre-calc class. There's another reason why a function could fail to have a limit, excuse me, when x is equal to c. And that's because the function will either increase or decrease without bound, which is a fancy way of saying you're going way, way, way up there or way, way, way down there, or approaching infinity or negative infinity. And the third and final reason is because a function might oscillate between 2 fixed values. Now, got a quick activity here as we wrap up the video. In the previous 4 examples, we discovered that 2 of those limits don't exist. We'll see if you remember which 2. And we're going to discuss, not so much with your table partner, but maybe with me, which of the three reasons from the box up above properly explains why those limits don't exist. Well, the great thing about this is that you don't have to remember those graphs because, boom, here they are once again in all of their beautiful glory. So, which two do you recall failed to exist? Examples 8, 9, 10, or 11? The answer is examples 10 and 11, right? Remember, this limit was 2 and this limit was 1. And so the limit in example number 10 doesn't exist, and the limit in example number 11 doesn't exist. But I want to match it with the correct reasoning. Why doesn't the limit in 10 exist? Because our fingers don't come together? That's not going to work on the AP exam. Yeah, unfortunately, you're never going to be able to say something so informal like the limit doesn't exist because my fingers don't come together. That's not going to earn points. You're going to have to use language kind of aligned with one of these three. You don't have to word them exactly. And so the reason that limit number 10 doesn't exist is because f of x approaches a different number from the left as it does the right. And you would just want to phrase that in some fashion. Don't say because of reason 1, because the AP exam reader won't understand what reason 1 is at your school. As far as graph number 11, the reason why this limit would fail to exist is because of reason 3. F of x oscillates. Now, whether or not f of x oscillates between two fixed values, that might remain to be seen. And I think maybe a better way to say this is that f of x oscillates kind of infinitely, and that might get a better explanation. But for right now, I'm going to allow us to kind of use this idea about oscillating between fixed values. We'll talk about what it means to oscillate between non-fixed values later on, which means you could have yourself a limit that does exist there. Now, as far as number 2, he didn't win any prizes with this activity, but if you look back at examples 6 and 7 from my previous video, you'll see a couple of cases where the limit didn't exist because of approaching an infinity or a negative infinity. Guys, I hope this helps a little bit. It's like I said, the most important part is how we ended this, and you really want to be strong with these reasons why a limit fails to exist. Just study them, practice them, use the materials that either I or your teachers are giving you, and it should definitely pay off down the road. We are still just starting our study of limits. So much more to come. We want you to tune into some more videos, but in the meantime, keep working, keep studying, and we'll see you next time. Take care.